All right, we have an electrostatics problem here. We have an isolated conducting sphere of radius 0.2 meter, and it's at potential of negative 2000 volt. For the first part, we want to determine the charge. This is supposed to say Q naught on the sphere. So for part A, we can just use potential equals K Q over A. So I'm just using the equation V equals KQ over R because this is a sphere, which is just like a particle when you're outside of the sphere as far as potential and electric field go. So if I solve for Q, we're going to get Q naught is equal to the potential times A divided by K, and then we can plug numbers into this. So potential is negative 2000 volt times that by A, which is 0.2 meter, and then we're going to divide by K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. So we can plug this into our calculator. Negative 2000 times 0.2, and then divide that by 9e to the 9. And I'm getting Q naught is negative 4.4 times 10 to the minus 8 Coulomb. So part B, determine, well, it says that the charged sphere is then concentrically surrounded by two uncharged conducting hemispheres of inner radius B equals 0.4 meter, outer radius C equals 0.5 meter, which are joined together as shown, forming a spherical capacitor. A wire is connected from the outer sphere to the ground and then removed. So this little bit of information is important. It'll change the problem quite a bit. And so we'll deal with that when we need to here in a little bit. So first thing to do is determine the electric field when R is less than A for part I. By the way, part 4, this is supposed to say where R is greater than C. When R is less than C, it depends on where you're at as far as what the electric field is. So R less than A, if you remember, for conductors, all of the charge will be on the surface. So this thing has a negative charge, and all of that negative charge is on the surface. If you were to apply Gauss's law, pick a Gaussian surface inside of the sphere, okay, the amount of charge inside of that sphere is equal to 0 because all of it's on the surface. Therefore, the electric field is 0. And for conductors in electrostatic equilibrium, the electric field inside the conductor is always 0. If it's not 0, then that means that charge is still moving around, so that's not electrostatics anymore. Part 2, we want to figure out the electric field where R is greater than A but less than B. So that would be this region right here. There's our Gaussian surface. If I apply Gauss's law, we have closed integral E dot dA is equal to Qn over epsilon naught. The amount of charge enclosed in that Gaussian surface is equal to Q naught. Okay, on the left side, we have closed integral E dot dA. This is the electric field everywhere on that Gaussian surface is equal, so we can write this as E closed integral dA. Take the electric field out of that integral, and then dA, the closed integral of dA is just the surface area of the sphere. So this will be E 4 pi r squared is the surface area of a sphere of radius r. So this thing has radius little r. Is equal to Q naught over epsilon naught, and then we get E is Q naught over 4 pi r squared epsilon naught. All right, part 3. in the region R greater than B less than C. That's this region right here. Same reasoning as before. We're now inside a conductor, which means the electric field has to be 0. So we can just say E equals 0 for part 3. So part 4 is the tricky part, R greater than C. And if it wasn't for this statement right here, then you would basically get the same answer as you got for part 2, except for R would be greater, right? Because you're outside of C. But as far as the equation looks, it would look exactly the same. But this statement changes things. So let's talk about what happens here. So before we talk about connecting the ground, we have this sphere that has a bunch of negative charge on it. And what that's going to do to the conductor that surrounds it is it's going to polarize it. Okay, so the outside conductor, all of the positives are going to want to end up on the inside surface, and the negatives are going to want to end up on the outside surface. Okay, and in order for this to be an electrostatic equilibrium, if I were to draw that Gaussian surface again in here, okay, we need the electric field in that region to be 0 so that the charge isn't moving anymore. And for that to be the case, if we have a charge Q naught on this surface, that means that the charge on this inner surface is negative Q naught, which means that the charge right here is positive Q naught, and this is kind of confusing, but we found this to be negative 4.4 times 10 to the minus 8 coulombs. Okay, and then what happens is we connect a ground to it, and when we connect a ground to this, the electrons are now able to get further away than before. So they're going to move to this larger conductor, if you want to think about a ground like that. They're going to move to this larger conductor and get further away. And then we're going to remove the ground. And so when we do that, remove this ground, these negative charges are gone. And what we end up with is a charge on the outside surface. It's no longer negative. We end up with a charge of negative Q naught on that outer conductor, which is equal to a positive 4.4 times 10 to the minus 8 coulomb. Okay, and so therefore, for R greater than C, when we draw a Gaussian surface out here, the amount of charge enclosed is equal to positive Q naught minus Q naught, which equals 0. Therefore, the electric field when R is greater than C is also equal to 0. Part C, determine the magnitude of potential difference between the sphere and the conducting, okay, so it must be the conducting shell. That part got cut off. Oh, there it is, conducting shell. So for part B, part C rather, we are going to use delta V, okay, and let me just erase all of this stuff again. When we find delta V and they say from potential difference between the sphere and the conducting shell, okay, finding the potential difference from this point, so at C going down to A, is going to be the same as if you found it from B going to A. And the reason is because we know the electric field is 0 in that region. E is equal to 0, and the magnitude of it is the derivative of potential with respect to R. Therefore, the potential cannot change as you go from C to B. So it doesn't matter what you pick your limits here. So what we're going to do for part C is find the potential difference as we go from point B to A. So I'm finding VA minus VB. I actually like to go out to in. So I'm going to go from B to A, from point B to point A. And it doesn't really matter because they are asking for the magnitude. So it doesn't matter which one you pick first. And so then if I apply our formula, we're going to have the negative integral a to b of E dot dr. The electric field here is the same electric field from what part? Part 2, right? We want this region right here. So that's part 2. And we found an electric field of Q naught over 4 pi epsilon naught r squared. And then we have dr here. So then we can pull things out of that integral so that we have negative integral a to b. And then we have a 1. Actually, I didn't pull anything out of the integral. We have a negative Q naught over 4 pi epsilon naught, and then in the integral we have a 1 over r squared dr. And that integral is going to be equal to negative 1 over r. And then we evaluate that from a to b. And then the two negatives cancel each other, and we're left with Q naught over 4 pi epsilon naught, and then we have a 1 over b minus a 1 over a. Okay, and we have values for all of these things. You could plug numbers in and get an answer. So go ahead and try that, but just to save time, I'm not going to do that in the video. Okay, last part. Part D, determine the capacitance of the spherical capacitor. So we are wanting C, capacitance, and capacitance is equal to charge over delta V. And so we're just going to do the charge that we have, which is Q naught, over the delta V that we just found. And so that's going to be equal to 1 over everything we just found. I'm sorry, let's do this. It's going to be Q naught over everything we just found. So Q naught over 4 pi epsilon naught, 1 over b minus 1 over a. The Q naughts cancel, and you could write this as 4 pi epsilon naught over 1 over b minus 1 over a. Okay, there is an alternate solution where they simplify this even more, but I don't like to do that just because if you simplify on the AP test and you make a mistake, then you might not get that point for your final answer. So I would just leave my answer like this. And I think that was the last part. Yep.